Goedemorgen, welkom bij de tweede presentatie van het Power Electronics event. In the studio there are Alexander and Marcel from Heynen. Welcome, Alexander from Germany.
Germany and the company Jianghai.
Yeah, okay, welcome. And good luck with your presentation.
Thank you.
Thank you.
Thank you. Good. So we start with the presentation.
Yeah, good. Good morning, everybody.
Good morning, everybody. I hope everything can see us. Yeah, shall we go directly to the presentation?
Yeah.
Okay. Good. Is it switching off now or?
No, you keep going.
Okay, good.
You're live.
So. Good. Yeah. Yeah, I can go forward. Okay. I'm sorry. Yeah, we start with a small introduction of the company Jianghai, that you know where is Jianghai and what we do, only a small part. And then we go to the main topics, the three technology of us, the aluminum-electrolytic capacitors, the film capacitors, and the energy capacitors. So let us start with a small about us. Jianghai is founded in 1958, in the beginning with electrolyte systems, and later in the 1970s with capacitors. And now we are one of the biggest manufacturer for film electrolytic capacitors, film capacitors, and energy capacitors. We have 13 sub-companies in the Chinese country for production, for pre-materials, for capacitor production, and also for terminals. So that's it for our company. About our products, as I described, we make our pre-materials by ourselves for each technology. We make the electrolytic capacitors, the film capacitors, and the energy capacitors. And we try today to introduce some technical details about each technology. And later I think there are many questions, and
in between questions.
In between we try to answer the open questions, and when there are much more questions, then we need another day to answer the questions. So that's it with the small introduction. Where do you use our capacitors? So you have the high-end class with DC link film capacitors for grid applications, wind energy, big photovoltaic, etc. Then the smaller parts, also solar systems, and the middle class of the power electronics, and then the smaller inverters with snap-ins, mainly electrolytic capacitors. And for e-mobility, there are different usings. Here in this picture, you see a DC link film, a small module, but many chargers are also produced with electrolytic capacitors. So, and for e-mobility, we have three parts in electric vehicles. We have the module for the inverter, for the drive, and the energy storage system, which also can use our capacitors for the main storage system. So the aluminum electrolytic capacitors. We start with a small pole.
Yeah.
You want to say something about the pole?
Yeah, it's interesting to know what are you using in your power applications, and where do you think you can use it in your power applications. And Alexander will explain afterwards the why, because of the voltage, and maybe something about pricing, what's happening in these systems using electrolytic capacitor.
Good.
A lot of answers are coming already. Mostly two.
50-50.
Are chosen the most.
Change.
I see a lot of things in the high voltage.
Yeah. And now we have both. 300 and 600. Now we are done. Okay. Good. The most are using the capacitors in the range of 300 to 400 volts.
I see one question coming.
Okay.
Maybe we can answer that. That's about the MTBF data. Maybe we can answer that at the end of this part.
Yeah. Okay. Good.
Or maybe it's already answered.
Yeah. I think this is a topic for later.
Yeah.
Okay. Good. Yeah. In this poll, we have no correct answers. You can use the electrolytic capacitor in each case, or for each voltage, but the technology have limits, and this is what we're talking about now. To understand where are the limits, we must know the construction of the capacitor. You have two foils inside the capacitor, the anode foil and the cathode foil. The anode foil is rotated and have a big surface, and you have the dielectricum, the oxide layer inside the holes of the surface, and this generate the voltage resistance and generate the capacitance of the capacitor. And to connect the cathode foil with the complete surface of the anode foil, you need the liquid electrolyte, which can flow inside the single holes and contact the complete surface. And this generates the high capacitance of the electrolytic capacitor. So, and this is one hole of the capacitor, and there you can see why we have limits to generate a capacitor with a high voltage resistance. When you produce the capacitor, you have in the first step a raw material aluminum foil, and then you etch the holes inside the capacitor to increase the surface of the capacitor, of the plate of the capacitor, and then you grow up the oxide layer. And when you make the oxide layer too thick, then you close the holes, and then you have only two plates and not more the big surface of each hole. And there is the limit of the capacitor technology.
Does this also have to do with voltage breakdown, or can you?
Yes. You need this oxide layer that you don't get a voltage breakdown.
Okay.
And therefore you need a thick oxide layer to resist the voltage.
Okay.
And when you use the capacitor at 105 volts and not at 85 volts, then you need also a thicker oxide layer to resist the temperature and the voltage together. So, and also important is the construction itself. On the right side is the new technology of etching the foils. When you control the process, you can make a better capacitor with a controlled capacitance, and the capacitor or the foil of the capacitor is more stable against vibration and make the capacitor controlled at the end.
So your complete foil production is like
on the right side. Yeah. This is the old design where the processes are not so specific and controlled, and later, since many years, we produce also the better foils with 140 micrometer.
This existed because you're working together with a lot of smart people in universities, or you did that? You changed that technique yourself in the factory?
We make it in our. We have joint venture with other manufacturers, Japanese manufacturers, and we develop this technology together.
Okay.
And now the big manufacturers use this kind of production.
And use your foil?
Sometimes they use our foil. This is what I said before. We produce the pre-materials and we make it for us, and we produce so much pre-materials that we can sell it to other manufacturers. So you can you have two philosophies in using foils in capacitors. You have the possibility to use it like the Jianghai philosophy. You use, for example, a 350 volt foil for 350 volt application, and this bring you the benefit that after the time you have a stable oxide layer and a stable leakage current after the lifetime. There's no much change after the using. But you can also use to save money, to reduce the cost of the capacitor. You can use the 350 volt formated foil. Can you use for 400 volts? It works as well, but the problem is after the same time you have a higher leakage current and a smaller oxide layer after the time, and this is the problem. The capacitor is not so long-term stable.
Okay, what then does the question was about the MTBF. What's the main reason when the capacitor fails? Is that in the application? Is it about the capacitance, or is it about, because you have a long-term application, you need a part working for 10 years.
Yeah.
With this, the part is changing its capacitance in a few years.
Yes. At the end, you have more healing need of the capacitor. When you have a smaller oxide layer, the healing need of the capacitor is much more compared to the thicker aluminum oxide layer, and this reduce the lifetime at the end of the capacitor, because you need much more water inside the electrolyte to heal all the breakdowns inside the oxide layer. There are cracks and after during the temperature the oxide layer will reduce, and then you need more healing to grow up the oxide layer.
Okay. Yeah.
So this foil is more interesting. You have typically a test period in development, and in the beginning, in this small area, you don't see if the capacitor have a poor quality or a good quality. You see it only after months or years. You see, okay, you have a reliable capacitor or a poor capacitor. And it's important that you make extended lifetime tests to see if you have a poor quality or a reliable capacitor. So the question should not be which capacitor have the lowest ESR or the lowest price. the correct question should be which capacitor has the best long-term stability. This is the correct question at the end. So,
can you tell me something about your production? What you're doing with the oxide layer? How you do that?
How we do it?
Yeah, that you go up to 79% of.
Okay, you mean
with the price?
This picture? Maybe. Yeah, you have. And the first step here, in the production, you have a formation of the pre-material, of the foil, of the pre-material of the foil, and then after the assembling, we have a second step after the impregnation. This is the post formation. And this is this step here. Some manufacturers produce or make the formation, the post formation, up to 90-70%, and save the money to make a formation up to 98%. The result is you have only the half energy to produce the capacitor. You save money in the production, but the problem is after the post formation, the oxide will reduce, and chemical reactions attack the oxide layer, and you lose oxide layer, and then after some time you have not so voltage resistant oxide layer, and when you start your device, then the leakage current is much higher compared to a component which is better formatted at the end, and sometimes some devices cannot work with such high leakage current in the beginning.
Okay, then continue.
So good. So there are some behaviors of the capacitors. Each parameter of the capacitor will impact from different outside impacts. We have the temperature, frequencies, voltages, currents, etc. And at different impacts, you have different behaviors of the capacitor, and therefore it's important to choose the right capacitor in the beginning of a design. And it's important to look what make the capacitor in this specific case, at this current, at this temperature, and what make the capacitor in the future. That makes what capacitance and what is not now, but what is in the end of the lifetime of the capacitor.
Is then still the product working, or is your application still
correct
in your in the values you want to have it?
Yeah, that's it. So there are some much more topics about electrolytic capacitors, but for the first step we are done with electrolytic capacitors, and in summary we have electrolytic capacitor with a defined lifetime, and it's important to choose the right capacitor, not when you look only on the costs, for example. It's important to look on the long-term stable high quality products, and not what is the cheapest capacitor, because you have different behaviors, and we call the capacitors, or the electrolytic capacitors, it's a living component. So let us go to the film capacitors. There we have also a poll. In which cases are film capacitors the better choice than electrolytic capacitors?
We are interested in what you think about which applications is the best choice to use film caps. One thing I must say, I discussed it also with Alexander at the beginning of this meeting. We have a lot of countries in Europe, and you see a difference between countries in using electrolytic capacitors or film capacitors. And some countries are more fond using electrolytic capacitors, and the others use a lot of film capacitors. Also has to do with manufacturing, I believe, and also has to do with the kind of engineers and the experience they have.
Yeah, so, that's it.
Yeah, you see a lot of answers already.
High voltage and low current. Okay. Okay.
Is that so?
Good. Interesting. Good. The truth is everything. It's okay for film capacitors, but our focus is on the high voltages and high currents, the high end of applications. So in comparison with electrolytic capacitors, to understand where are the difference and why we use it in such applications, you must understand the construction or the difference of construction in both technologies. Here at the electrolytic capacitors, you have a complex design, the cathode foil, the electrolyte, the anode foil with the oxide layer, and separator paper inside the capacitor. It's very complex, but the benefit is we have a very thin dielectricum and a big surface in this capacitor. And by the film capacitors, we have a simple construction. You have only the plastic film foil and the metallization plates outside the plastic, the anode and the cathode metallization. And here can you see it on this screen? We have a big dielectricum by the film capacitors and a very thin dielectricum at the electrolytic capacitors, and this results in a higher capacitance at the electrolytic capacitors in the same case and dimension of the component. So in numbers, or at Jianghai, we have two different areas. The low voltage up to 650 volt is for the electrolytic capacitors, and when you need a high voltage product, then we offer only the film capacitors, because at over 650 volt, it makes no sense to produce electrolytic capacitors, because you need much more energy to produce a thicker oxide layer. And this is what I explained before. You close the holes inside the foil, and then at the end you have only the same thing like the film capacitors, only two plates, and in the middle one big dielectricum.
So a very low capacitance.
Very low capacitance, and then you have a much more expensive capacitor with no better behavior like film capacitors. So in fact, you have in the same dimensions and for the same voltage around 3 times higher capacitance for E-caps.
That's not similar like the...
No, it's not the similar product. there's a 600, and here we have 2000 volt. It's not the same thing, but here we have this similar, but here is not it's only a picture, but this is a 450 volt. But in fact, we compare 600 volt capacitors and a K size from 7070 to 96. And you see the capacitance of the electrolytic capacitors is 3 times or more than 3 times higher compared to film capacitors. But the benefit from film capacitors is the current behavior. You have a stable current over the complete temperature range of the capacitor. And for ECAPs, you have the possibility to use the capacitor with higher temperatures as specified. That means usually the capacitor is specified at 85 degrees, for example, and then the current and the temperature increase during the current is up to 95 degrees. And for film caps, we have specified 85 degrees, and this is including the current. That means when you have 85 degrees in the ambient temperature, it's not allowed to use current, because you increase the temperature inside the capacitor, similar to the ECAP, but this is the technology difference between ECAPs and film caps, that it's possible to use current over 85 degrees, and for film caps it's not possible to use currents over the specified temperature. Okay. But the currents under the specified temperature are much higher compared to the ECAPs. Okay. In the same case, and with a much lower capacitance. Yeah. So further benefits of the film capacitors are the stability at different impacts. Here, the temperature performance, the ECAP change everything. The capacitance is changed, the ESRs change, the impedance is changed, everything is changed at different temperatures, minus and plus, everything is changed. For film caps, nothing is changed. The capacitance is stable, and the tangents, the dissipation factor is stable. Nothing is changed. Not at minus temperature, not at high temperatures. Okay. The same for frequencies. For frequencies, especially at high frequencies, the film caps is also stable. Nothing has changed. The capacitance is have a stable capacitance. The dissipation factor is stable over different frequencies, and on the other side, the ECAP is changed. His capacitance and his dissipation factor at different frequencies. And therefore, we use film capacitors in the high-end application with high frequencies, high currents, and high requirements of the application.
Can you name one of your applications you have for this kind of high-end? What kind of?
Yeah, the big inverters for chips for wind energy, for each expensive inverter technology where you need a very long lifetime and a long time stable capacitance, which is stable over the complete lifetime. Here you can see the capacitance change over the lifetime. By at film capacitors, we have at the end of the lifetime only 3% capacitance loss. For ECAPs, we have at the end between 20 up to 30 or sometimes 50% capacitance loss after the lifetime. Okay. And we start here with 70 degrees and 100,000 hours. This is the normal specified lifetime of film capacitors. And for ECAPs at 70 degrees, we have maybe the half lifetime.
Okay.
But at the end of the lifetime, a much higher capacitance loss.
Okay.
And this is the reason why you use film capacitors when you need a long-time stable component. So the failure modes are quite similar. You have the thermal failures from the ambient or during the current increase of the temperature. You have the electric breakdowns, but the difference in failure modes for film capacitors is the moisture corrosion. This is not so important for ECAPs, but for film caps. And therefore, we have several changing inside of our capacitors. We use different filling materials for the aluminum cans. We use PU, different PU fillings for the modules, and for the small DC links we use epoxy. And also important is the terminal design. In the past, and some of our competitors use flat terminals, and we use terminals with a longer path for the moisture to reduce the impact of high humidity outside the capacitor, that the moisture needs a longer time to come into the capacitor. So, also interesting of our film production is are the modules. You have the benefit between a DC link cylindric type and a module like this or like this. You can reduce the ESR, the ESL, and you can use much higher currents in the same capacitance and voltage. And the additional benefit is you can put the modules directly on the EGBTs. We have different designs. On the next page, better to see. We have different designs for different EGBTs and different applications. And the most of them, we have hundreds of them, are customized.
And there are some specially used for special modules from certain suppliers.
Correct. Yeah, and this is the internal structure of such module. Bus bars, which are connected to anode and cathode, and then we can make a parallel circuit. We can make a series circuit of the single cells inside of the capacitor to generate the specific capacitance and voltage what the customer need for his application. So, in summary, we have very high voltages for this.
Yeah.
You have a question? Okay. High current and low ESR, and a very long lifetime. And this is the main difference between the technologies, between the electrolytic capacitors and the film capacitors. So let us go to the last technology, the energy capacitors. Normally you think, when you think about capacitors, you think about input filter, DC link, buffer, etc. But the less people think about the energy storage system. So the energy capacitors are including two technologies by Jianghai, the double-layer capacitors and the lithium-ion capacitors, and depends on the requirements of the application from the customer. We choose is lithium-ion the better choice or the double-layer capacitors. But I think the most of you don't know or know the EDLCs, but don't know the lithium-ion technology. And the benefit of the lithium-ion technology is they close the gap between the EDLCs and the battery systems. Here in this free space, there are the lithium-ion capacitor located. In numbers, you have the EDLCs with a very high charging rate, very many cycles, and a limited energy density of 5 to 7 watt-hours per kilogram. With lithium-ion capacitors, you have the benefit of the high cycles, but with reduced the charging rate. It's high compared to batteries, but it's less to EDLCs. The benefit from this technology is the much higher energy density, which between 40 to 50 watt-hours. And batteries have the typical disadvantages, low cycle numbers, low charging rate, and the safety for lithium-ion batteries is under discussion. So we have a last poll. In which power application will you use a capacitor as energy storage?
Can you think about using it?
Yeah. Maybe you use a capacitor as energy storage, or you are interested in one of these four possibilities.
Maybe a difficult question.
Oh, do you have the possibility to click in the presentation, or is it only possible for me? Because we need the click on the different slides. We need a click on A, B, C, or is it possible for our moderator? Okay, I see it. What is e-mobility?
Yeah, e-mobility.
E-mobility, okay, then I click here. Sorry, I see it here now. Okay. E-mobility, good. The answer is sorry? Okay. E-mobility, you can use the capacitors in each area, which we showed before, but for you was the e-mobility more interesting. Here we have put one of our e-mobility applications in this presentation. Here we compare the lithium-ion battery bus with an energy bus, an energy C bus. So
it's a real bus in China.
In China, this is a real project in China, in Jianghai, more precise. They use in the past lithium-ion battery buses with a big pack of 3.4 tons and a range of around 120 kilometers, but with a charging time of 4 to 6 hours. And they change this battery module against a capacitor module, which is much lighter, smaller. You reduce the volume of the pack, but the disadvantage is the range. But this the benefit of this reduced range is the charging time. The charging time is much more reduced. We have time at each station to charge the capacitor. It's more clear when I go to the next slides. By battery buses, we have one bus which can drive on the route from station to station, and when the module is empty, then it goes to the charging station, and the next bus which charge before, go to the next run and transport the passengers. You need much more buses to fulfill a 24 hours station using in a city bus. And you need a separate charging station for the empty buses, and the problem with safety in the passenger transport systems. With energy C buses, you have the benefit that you only need one bus for the same route of the transport in the city. And at each station, you have the time when passengers enter the bus and leave the bus, you have the time to charge the module. And this is maybe 1 minute, but it's enough to reach the next station. And then you can drive the 24 hours, 7 days in the week, and 365 days per year.
You only need to change the bus driver.
Maybe when you have a good bus driver or a roboter, automated guided bus, maybe then you need future.
Yeah.
It's true, but for the future we have now the correct or the best energy storage to fulfill this using. The benefit is the high cycle numbers, the environmental friendly benefits of this technology compared to lithium-ion batteries, and it's safe. And in the case of an accident from the bus, we have not the problem that the capacitor burn or explode or something else.
Okay. Yeah, the other applications are also in the presentation, which you probably receive afterwards. You can read it down. And if you need more information, I think Alexander has more details.
Of course.
To show or to present to you personally.
Okay, I think we are at the end.
Yeah. Maybe. Okay.
Yeah.
Okay.
We have no more time, I think.
Oh, when you want, you can have it's. Oh yes, when you need a few minutes, it's okay.
Okay.
Go back
then I go back.
Yes.
Okay, good. Then I show you some roadmaps of the booth technologies, the EDLCs. In the future, we plan to make cells with a higher cell voltage up to 3.4 volts and a double lifetime and a wider temperature range in the future. For lithium-ion capacitors, at the moment we are at 80. Before 2022, we are now here at the 80 watt hours. Currently, we have cells with the energy density of 80 watt hours per kilogram. We are better than the roadmap here. But in the future, we try to close the gap between batteries and capacitors more and more. And in the future, maybe we reach the 100 to 120 watt hours per kilogram. And we want to increase the temperature range of the capacitor. Now we are at minus 25 degrees, but we try to make cells with minus 40 degrees.
What do you expect is the maximum capacitance you can reach with these kind of techniques?
The maximum capacitance per cell?
Yeah, you have a limitation maybe on your physical limitation at the end, or is that still not?
Yeah, it's depends on the using of the cathode and anode materials, of the pre-materials. Mm-hmm. You use active carbon or graphene, etc. There are the limits in the pre-materials. Okay. And the biggest cell what we produce now in in this design, this is the old one, 16,000 farads in this cell, and with the new series we get in the same case, in the same thickness, 25,000 farads.
Okay.
In the same case. Now,
Thank you. Thank you very much.
This is a small view in the future. Good. I think we are done.
Yeah. Alexander, thank you very much.
Thank you, Marcel.
And
thank you, the whole team here.
if there are questions, you're welcome to ask them. If you have questions afterwards, please send it to us. And then we are happy to ask them or to answer them and to maybe make an appointment to give some more details, which we have.
Yeah. We offer also trainings for each technology, for the ECAPs, for film caps, and also for the energy capacitors. And there you can learn everything of the technology.
For engineers.
For engineers, it's not for salespeople like us. It's for engineers.
Yeah, okay. Thank you.
Now, thank you very much, Marcel and Alexander, voor de presentation. En u allemaal bedankt voor het kijken naar deze tweede presentatie van Heynen en Jianghai. Om 11:30 begint de volgende. Dus, en het hele programma natuurlijk verder nog vanmiddag, morgen en donderdag. Kijkt u vooral op de website. Bedankt voor het kijken en graag tot de volgende. Dankjewel.